ladies and gentlemen, please welcome Assistant Professor at ETH, Anna Klimovic. Anna, thank you.
Hello, everyone. Thank you very much for having me. So my name is Anna Klimovic, and I just started as an assistant professor at ETH Zurich last year. So today I want to take you behind the scenes of building computer systems for cloud computing. This is the topic of my research with my students at ETH. So the amount of data that we're generating, storing, and processing is growing exponentially. And we're increasingly doing this in the cloud. Why? Because cloud computing promises high elasticity, which means as we need more resources, we can get them incrementally from the cloud. And as we start to need less resources, we can let go of them and do this in a cost-efficient manner. We can scale our computing and our storage resources as our load grows. And we can achieve high performance because we get access to high-performance servers and networks in the cloud. Now, one thing we're assuming here, in order to achieve these elasticity, cost efficiency, and performance goals, is that we can give each cloud application the right amount of resources that it needs, in terms of both computing power and storage. And it turns out figuring out this right amount is quite challenging, because we want to give applications enough resources so that they can achieve their peak performance, so they're not bottlenecked on either compute, network, or storage. But we don't want to over-allocate resources so that we're just spending extra costs but not really getting any additional performance for those resources. And so it turns out that figuring out the sweet spot of how much resources to allocate to an application is really challenging, and it makes achieving these goals of elasticity, performance, and cost efficiency difficult. So what I hope to do today in this talk is take you a bit behind the scenes of these kind of facilities. And to talk about designing computer systems at this kind of scale. This is a data center, so we typically have tens of thousands of servers in one of these kind of rooms, burning tens of megawatts of power. And it's these kind of facilities that are powering services we're using every day, whether it's search, social media, video streaming. Or we can be using platforms from public cloud providers like Google, Amazon, and Microsoft, where we're renting cloud resources and running our own applications. So the actual technology, or one key part of the technology powering the cloud, is virtualization. These cloud facilities have tens of thousands of physical machines. These are servers with some amount of CPU, memory, and storage. And virtualization is the technology that allows us to make a single physical machine exposed to users as multiple virtual machines. And this is powerful because we can share resources more efficiently. We can run the applications for multiple different users on a single physical platform. And we can do so in a secure manner, isolating the information of each of the user's applications. And this is kind of the first step that the cloud really relies on, is this ability to share resources and virtualize them. So I'm calling this Cloud 1.0. The next thing that the cloud allows us to do, and this is sort of the traditional model of cloud computing today, is these virtual machines being rented at fine time granularities. So it started off by you could rent a virtual machine for an hour. More recently, you can rent them for a minute or even per second. And so you can say you have different applications. Here we have an example of MySQL and Cassandra. These are databases, Rails and Nginx web apps, and Hadoop data analytics and storage. So depending on what type of application you want to run, you can say, I want this type of virtual machine that has a certain amount of CPU, memory, and storage. So as a user, you can decide what configuration is right for you and how many of these virtual machines you want to rent. The advantage is the cloud provider is the one who's actually powering these machines for you, and you just have to, you don't have to manage them, you just have to decide how many of them you need and what you want to run on top of them. Now, what's interesting here is although that gives you better cost efficiency, the cloud provider is amortizing this cost of managing all the servers, you still have to think in terms of hardware. You have to decide what is the ratio of resources that your applications need. And so one thing that's kind of happening right now in the cloud computing space is this shift towards what's called serverless computing. It's a bit of a misnomer. Has anyone heard of serverless computing? Can I get a show of hands? OK. So it is a bit of a misnomer because there's definitely still servers involved. Your code has to run somewhere. But the idea is the cloud providers today are moving to a model where we raise the level of abstraction because this management of thinking, OK, how many CPU cores do I need? How much memory? How much storage? How should I schedule my applications? All of these things are very difficult for users to reason about. And the goal is to make the cloud accessible to anyone. So we want users to just specify the tasks that they actually want to run. So this is the code that needs to run and the event that should trigger this code to run. So perhaps some sensor data becomes available, some data is loaded into a database, and as a result, we want to process some computation. And so serverless computing is a kind of new execution model in the cloud that allows users to just specify the task that they want to run, and the cloud provider automates where that task will actually execute and how many resources it will take up. Meanwhile, the user is just charged for the actual computation time on the particular resources. So again, this is kind of making things more cost efficient, assuming the cloud provider automates this all in a proper way. This is making things higher performance because the cloud provider is in charge of allocating that right amount of resources. And we're also increasing elasticity here because these tasks can be extremely fine-grained. And actually, on today's serverless computing platforms, examples are Amazon Lambda, Azure Functions, or Google Cloud Functions. You are actually charged per millisecond for the CPU resources that you're using. So why do we want to automate resource allocation? Or why do we, I'm speaking kind of as a cloud provider perspective here, why automate resource allocation? It's because it's really difficult for users, as we've alluded to, yet it's absolutely critical for performance and cost. So I want to try and give you a sense of why resource allocation is difficult and why it's a good idea for cloud providers to be automating this for users. So here's an example of an application that ran at Facebook. This is several years ago now. This is actually data I collected as an intern at Facebook back in the summer of 2015. But the general trend is still true today. So what we're seeing here is resource utilization over time for a service at Facebook. So you can picture this as, for example, a newsfeed service or something where you have some database that you're querying, but you're also doing some processing on that data. And we don't need to go into all the details of this graph, but the point is that over time, we see that CPU utilization in the green line is varying dramatically over time. And then storage, both in terms of capacity and bandwidth in the orange and blue lines, is also varying over time. So these resources are dynamically varying, and if you're trying to decide, I need to run this service, which virtual machines should I use? And how many of them? And how should I kind of schedule these tasks on a bunch of resources? There really is no right answer to get things perfectly right, because this ratio of resources that you need is changing over time. And typically, you're not just running one service, you're running multiple. And if you look at the resource requirements of different services, those will also differ. And finally, storage and compute resources are not necessarily correlated. So there's this moment in the middle of March where CPU utilization dropped significantly, and that's actually because the algorithm became more compute efficient. But the overall load on the service continued to grow, and that's why storage was still on the rise. So the fundamental problem here is that resource requirements vary dynamically over time, but the physical machines that we actually run our code on have a fixed ratio of resources, right? When we build the hardware, we have to decide how many CPU cores, how much memory, how much storage. And so inevitably, this leads to an imbalance in resource usage, and therefore, we're underutilizing the physical machines in the cloud. And here's an example. Flash storage is underutilized for long periods of time in this particular example. But just to convince you, this isn't just a problem in this particular service that Facebook was running in 2015. This is a problem in general today. A lot of the cloud resources and servers are dramatically underutilized. There's multiple studies from Google. This is the most recent one from 2019 that they published, where they show CPU usage, this is on the left, and memory usage on the right over time. And this is actually considered state-of-the-art, right? Google is very much interested in completely optimizing utilization, and yet still there's opportunities to grow in terms of how well we're utilizing the machines in the cloud. This also affects how much energy we require to do this type of computation. So what can we do to improve utilization, given that we have to accommodate applications that have very diverse and dynamically changing ratios of compute, memory, and storage requirements? So today we have this model of servers. This is how the hardware actually looks. We have a schematic of how it looks. We have physical machines that have a fixed ratio of resources. What we'd like to move towards, even if the actual hardware looks like this, with these fixed ratios, what we want to do is allocate resources in terms of resource pools. So logically, we want to think of all the storage as one pool, the CPUs as a pool, the accelerators like GPUs that are commonly used for machine learning as a pool, memory, and all of these are interconnected by a fast network. And this is already the case today. The networking capabilities of the hardware are very good. There's still room to improve on actually making sure we can get that bare metal performance from the software stack that runs on top of the hardware. So what we'd like to do is have a logical view of resource pools, and then as different applications come in, we dynamically allocate the right ratio for each application. And here's an example of 3 different applications that can have different resource ratios they require. And so ultimately, what the cloud provider wants to do is make these allocations from resource pools. But again, these things are difficult for users to do, and this is where we come back to this idea of a higher level abstraction for the actual user involved. And this is kind of this model of serverless computing, or more broadly, I'll call it cloud services, where serverless is also called functions as a service, but there's all kinds of as-a-service things in the cloud. You can have machine learning as a service, where different aspects of ML training are automated, and storage as a service as well, where your storage scales and you pay just for the amount of data that you have as your data grows and shrinks. So there's all kinds of interesting questions as to, and challenges when it comes to designing systems with these goals in mind. Building balanced systems, one question is, how do we design fast communication between all these components, right? If we still have hardware that's going to be, we're going to be accessing hardware on different machines, but we want to, for a single application, make sure all the components within a data center, or maybe even across data centers, are efficiently communicating together. We also need policies for deciding how to schedule these applications. So how do we decide that this particular task should run on this server, and a different task should run on another server? So we need to take things into account, not only how much does each task require in terms of resources, but how do these tasks perhaps interfere and compete for resources. Another set of questions related to this abstraction or cloud services is, what is the right level of abstraction that users should interface with the cloud? Serverless computing, or this idea of the user just submits a function and a trigger for when that function should execute, is one kind of newer model that has emerged. But I think there's actually a lot of room here to explore different layers of abstraction that provide both ease of use, but also allow users to get predictable performance and specify actually what are their performance requirements. And then, given that we're going towards a finer and finer granularity, where users now don't think in terms of machines, but they think in terms of individual tasks, the cloud provider also now needs to take those individual tasks and schedule them all, and potentially packing thousands of tasks onto a single physical machine. So there's a lot of interesting questions with how do we build operating systems that can actually efficiently schedule these things. If we think of the operating system like Linux, it wasn't designed to run thousands of threads from different users isolated on a single machine. So these are examples of the kinds of research questions that I'm working on in my group at ETH. We're called the Efficient Architectures and Systems Lab. And we're part of the systems group at ETH, which is a group of multiple faculty broadly working on computer systems. And we interact with industry a lot. And if you have some interesting use cases that emerge in terms of building computer systems at scale, we're always interested to hear from you. So with that, I'll conclude, and I'm happy to take questions. Thank you.